Right. Our next talk is by Pei Wu, and its title will be explained to us.
Good afternoon, everyone. Yeah, thanks for coming. And the title is "This It and Over Till It's Over." Well, I don't know. Maybe if you are curious enough to search on Google, you may find a pop song. And don't worry, or maybe don't be too hyped, because this is not going to be a talk about pop song. So I will unveil the mystery of this title during the talk. So I guess in the end, if you still think it's a title of pop music, then I know that you only listened for the first 30 seconds of my talk. Okay. So this talk is actually about Boolean functions. So we have functions mapping from the Boolean hypercube to 0, 1. And we should always think of functions as a family of functions. So n can goes to infinity. And first, I want to introduce this notion of influences, or maybe you have heard another name about it, which is called Bazak index power. If you haven't heard about it, this is its definition. So for every variable or for every bit, its influence with respect to the function f is just a probability, the probability that you flip the function value by flipping the corresponding variable on a uniformly random input from the Boolean hypercube. And the max influence is just the max over all the individual influences. And to help us digest this definition, let's look at two canonical examples. And we will see that these examples are not just random examples later. So the first example is the majority function. It outputs the majority bit from its input. And its max influence is 1 over square root of n, and this notation just hides the constant. And why is this number? It's very simple, so let's look why. For any variable, if it's sensitive, meaning by flipping this variable, you flip the value of function, then it has to be the case that this bit is a majority bit, and also in your input, the number of zeros and number of ones differ by at most 1. This is example 0, 1, 0, 1, 0, 1, 0. And then in 0 is sensitive, you flip the 0 to 1, you get, you flip the majority bit. And then the probability that a random string has approximately equal number of 0 and 1s is about 1 over square root of n by Stirling approximation. And conditioning on that event, any bit to be a majority bit has a probability at least a half. Okay, so that's the majority function. Any questions?
So theta, the theta function, what is theta?
So it just says this thing is about 1 over square root of n. That hides like a square root of pi. So I hide some constant. So there should be some constant, but we don't care about constant.
So inequality in both directions.
Yeah. Maybe I should just write approx. But this is a notation for computer scientists. Okay, so I revealed my. The next example is the tribes function, and this is the logic OR function composed with logic AND function composed with logic OR functions. The AND function outputs 1 if all its inputs is 1, and the OR function outputs 1 as long as one of its input is 1. And the parameter is set so that the function will output 0 or 1 with approximately half probability of random input. So in particular, the n will take about n over log n inputs. That corresponds to n over log n number of OR gates. And each OR gate will take about log n minus log n inputs. All the OR gates share disjoint inputs.
So what does this notation mean? Xij.
Okay, just means it's different inputs. So there are like n number of inputs, but I want to make sure that they are different inputs. So the subscript just denotes it's a different bit. It's like x11 is input is 1 bit, x12 is another input, another bit.
Here, n is equal to s times w.
And yes. Yes. Okay. And the max influence of this function is about log n over n. I have some constant again. Well, also let's very quickly check why is the case. So here, let's just focus on the case where the inputs output 0.
I'm sorry, but if n is equal to s times w, why w is not, I mean, and s is equal
Yeah. Sure. Sorry. So here maybe you want to write n over log n minus log n. Yeah. But sorry. So maybe it's a bad habit for us.
It's a computer somewhere.
Yeah. So like only the largest order term matters for us. Well, at least for me. Okay. Yeah. So let's see why the choice function has influence of this order. And we are just going to look at the case where the output for the choice function is 0. And then in this case, if a bit is sensitive, then it has to be the case that there is exactly one of the OR gate that outputs 1. So that by flipping the input fed into this special OR gate, you flip the value of your function. And you can easily calculate that on a uniformly random input, this event happens with constant probability. And conditioned on this event, like for any variable, it is an input to this special gate. Is a probability like log n over the entire length of the input, and that's what we get, log n over n. So these are the two examples. I hope it clarifies the definition. Okay. And now we can see that the above two examples have the following property. So their max influences are very tiny. They are polynomials small with respect to the input size. Okay, and we are going to in addition to assume that the function outputs 0 and outputs 1 with approximately same probability. So half and half. This is just for simplicity. But maybe you are complaining why we care about functions whose max influences are small. It seems to be a very restricted family of functions. So let me explain. So first, they actually arise very naturally in many different applications. The first application is the social choice theory. So let's say during the weekend, maybe after this talk, you and your friend are going to hang out together, and maybe you can play games at home or play soccer on the grass. Each of you will have your own preference, and you want to reach a consensus. What you can do is maybe take the majority preference. But you can do a more complicated thing, like to vote for the president. What we do is we take the majority vote within each state, and we aggregate the votes from all the states based on the weighted majority. And you can, of course, design your own voting scheme. And you may want the voting scheme to satisfy certain properties. And it's very, very reasonable, I guess, in most scenarios, that like no individual can decide the outcome. regardless of the other people's preference with high probability. And that is captured by this notion of maximum being small. Okay, and the second application comes from computer science. The hardness of approximation, or the PCP theorem that you may have heard about once or twice this week. So we know that you can organize a proof and you only need to verify a random constant number of locations of proof, but you have to structure proof in a certain way. And then maybe you want to check your proof is indeed structured in this way. And somehow, in the end, it is reduced to the task to test whether a function is a dictatorship function, meaning there is an individual bit that decides the outcome of a function, or your function satisfies that all its bits has more influences. And the third reason why this kind of functions are interesting is due to the so-called invariance principle, which is saying that for functions like this, you can actually replace a Boolean random variable with any random variables that has the matching first moment, second moment, and bounded third moment. And the special case are something that we are all familiar with. If we have the central limit theorem, if we have this linear function, the sum of independent random variables, where non-random variable is too dominant, then their sum behaves like a sum of independent random Gaussian variables, which in itself is a Gaussian. So that's the third reason. I hope these are enough motivations for us to study this kind of function. Okay. And finally, I want to introduce another notion. In computer science, we call it random restrictions, or maybe we can call it the random subfunction. To be concrete, so we are going to take our input and we are going to restrict the input in the following manner. So for each variable, we are restricted independently with probability p. And when we restrict the function, we fix it to 0 or 1 with half and half probability. So in the end, only like 1 minus p fraction of inputs are not fixed, and that gives us a subfunction. Now with these two notions, we have a very natural question. That is when we apply random restrictions to the class of function we're interested. So the class of functions where no input bits has large influences, then what happens? So in this work with Alden, Wigderson, we prove the following. So if we restrict all, but a slightly larger than 1 minus log 1 over the max influences, then the function, the restricted function, will be non-constant. Will be non-constant almost surely. So recall that for majority and for Travis function, the max influences is polynomially small, which is kind of saying that we can restrict all, but a fraction of 1 over log n inputs. And this is the best we can do. Exactly because of the Travis function. For the Travis function, if we restrict all but 1 over log n, which is which corresponds to its max influence, then we are going to get a constant function with high enough probability. This is the first part, and the second part is that here the statement that the restricted function being non-constant is a quantitative statement, and we can prove it into a quantitative statement. So we can show that the function is not only non-constant, but actually far from constant function with high probability. So I have no intention to say what's the exact quantity here, but what I want to tell is that this matches the behavior of the majority function. So in this sense, this is also the best we can achieve. Any questions? Okay, well, maybe a few more remarks. So a related problem is first asked by Friedgart and Kalai. They formulate the problem and call it n over till it's over conjecture. Yeah, so they're interested in restricting your functions, restrict all but an arbitrary small non-zero constant fraction of the inputs. And they want to say that the restricted function is mildly balanced with high probability. Okay, and the original conjecture is actually proved by Morse, O'Donnell, and Oleszkiewicz in 2010. So in our work, we make a short version of the theorem. And I also want to mention that around the time we obtain our proof, another group called Lifshitz-Miller, also they have a different approach. I think this is quite amazing that like over 1 decade, there's no progress about this problem, but somehow at the same time, we have different approach to make this result sharp. Okay, so finally, let me spell out a few words about our approach towards this problem. So we are going to consider the following again. So we are going to expose the value of our variables in a random order. In particular, fix a random order and from time 1 to n. When a variable comes, we expose it as follows with probability 1 over 1 minus epsilon. The variable will be fixed uniformly at random. So it's going to be 0 or 1 with half-half probability. And with the remaining probability, the player gets to decide what's the value of the function. So you can do whatever you want, but the goal is that in the end, the string we get, we want it to be a uniformly random sample from the pre-image of 1 for this function. Well, if you think about it, maybe you realize this is too ambitious because like if in the end of the game, the player don't get to decide, don't get to control, then basically there's nothing you can do. So what we do is we modify this game a little bit. We just set a time m. So we say that before this time m, we do as what I described with probability epsilon that the player gets control. And after the time m, then we grant the player full control. She can do whatever she wants after the time. And the key point is that in total, we can prove that the player only needs to control about a fraction of 1 over, like log 1 over the max influences, fraction of the inputs. So to sample the input, that is a uniform random per image of 1 for this function. So that's what we can prove. And why we are doing this? Well, this is because for the time prior to time n, we can view those coordinates, those variables that's not fixed by the player as the variables decides our random restriction. And then what the player is doing is to sample, not just to obtain a pre-image of 1 for this function. And analogously, we can definitely show that the player can also obtain a sample of the pre-image of 0 for the restricted function. And all in all, just saying that after restriction, the player can get both 0 and 1 from the restricted function, which is just saying that function is non-constant. And the fact that the player can not only obtain one sample, but can actually do this uniform sample, help us to analyze the variance of the restricted function. Okay, my talk is over. Thank you.
Questions? Okay, thank you.